Good morning, dear students.
Good
Good
afternoon,
morning, sir.
sir. Good.
Good afternoon. Uh, Let us revise what we have studied yesterday. We have seen the various methods for the preparation of the aldehydes and ketones. We uh, we have studied about the diol H. The full form of diol H is diisobutyl aluminum hydride. This diol H converts nitriles to the aldehyde. The nitriles are converted to the aldehyde by diol H without affecting if there is any unsaturation present into it. So diol H selectively converts nitriles into the aldehyde. Same way, diol also reduces esters to the aldehyde. So you can see here that an ester with 11 carbon, not 11 but 13 carbon, is simply converted to 11 carbon aldehyde by its reaction with the diol H. Same way, my dear students, we can study about the various methods of preparation of benzaldehydes. You can see that benzaldehyde is prepared by the various methods. In a method called Rosenmuth reduction, acyl chloride or acid chloride is used. So here we use the benzoyl chloride. Benzoyl chloride is hydro benzoyl chloride or acid chloride is hydrogenated to benzaldehyde in the presence of palladium and BaSO4 catalyst. So this is how, my dear students, we understand about the uh, preparation of our benzaldehyde. You can see that the benzaldehyde can also be prepared by some other methods. The various other method that we can see the Stephen reaction. In the Stephen reaction, nitriles are reduced to imine and imine then hydrolyzed to aldehyde. So here we have cyanobenzene that is allowed to react with or that is allowed to reduce with the stannous chloride in the presence of hydrochloric acid. We get an imine which is hydrolyzed to give us the benzaldehyde. Same way, my dear students, a very important reaction which is known as the Itard reaction. In Itard reaction, toluene is converted to benzaldehyde. Toluene is allowed to react with the chromyl chloride, so it gives us the chromium complex. And this chromium complex on hydrolysis gives us benzaldehyde. Same way, in another reaction, toluene is allowed to do or undergo the side chain chlorination, so we get benzyl chloride, which on hydrolysis gives benzaldehyde. Same way, in third reaction, toluene is allowed to react with the chromic oxide and acetic anhydride at 273 to 283 Kelvin temperature, so that we get the benzylidene diacetate. This benzylidene diacetate on hydrolysis gives us the benzaldehyde. And in the last reaction, that is known as the Gattermann-Koch reaction or Gattermann-Koch synthesis, we can prepare or we can convert the benzene directly into the um, benzaldehyde by the reaction of benzene with the mm, with the carbon monoxide and hydrochloric acid in the presence of anhydrous AlCl3. So this is how, my dear students, we can easily understand the various methods of preparation of benzaldehyde, uh, and that is what we have seen it. Now, my dear students, Let us move forward and study the next portion of the chapter. So before we move to the next portion of the chapter, let us understand it well that here we can see, let us share the new screen. Now, my dear students, we want to study about the preparation of ketones. So let's have a look at the preparation of ketones. We can prepare the various ketones by the various reactions. First, we should look at the preparation of ketones from the acyl chlorides. So let's see how ketones can be prepared from the acyl chlorides, my dear students. The treatment of acyl chloride with dialkyl cadmium prepared by the reaction of cadmium chloride with grignard reagent gives us ketone. So let's have a look to this particular reaction, dear students. Let's just see the reaction steps. Here in this particular reaction, you can see that we have a Grignard reagent RMgX, which is allowed to react with the cadmium chloride. So we can get dialkyl cadmium. We shall call it dialkyl cadmium. This dialkyl cadmium undergoes the reaction with the acyl chloride, and as it undergoes the reaction with the acyl chloride, it gives us the ketone. And the catalyst cadmium dichloride is obtained in the same form, and that is why we can say that CdCl2 behaves as a catalyst over here. Let us understand this reaction with one example. We want to prepare acetophenone. So to prepare acetophenone, we can take phenyl magnesium bromide. This phenyl magnesium bromide is your Grignard reagent. So this phenyl magnesium bromide undergoes the reaction with the cadmium chloride, and it gives us the diphenyl cadmium. This diphenyl cadmium undergoes the reaction with the acetyl chloride, and gives us acetophenone as the product. So this is how, my dear students, using the acyl chloride, this is what we call it, acyl chloride, and then by the use of the cadmium chloride, we can prepare the required or desired ketone using this catalyst. Now, my dear students, we want to study the preparation of ketones from the nitriles. Let's see how from the nitriles we can prepare the ketones. Treating a nitrile with Grignard reagent followed by the hydrolysis yields ketones. Once again, we need to take nitrile, then you need to allow it with the react with the Grignard reagent, and then we go for hydrolysis. So this is what we can say about the nitrile. This is the nitrile that we have. This nitrile undergoes the reaction with the phenyl magnesium bromide. When it undergoes the reaction with the phenyl magnesium bromide, it produces an intermediate, you can see here. So you can see that this triple bond turns into double bond between carbon and nitrogen, and with nitrogen, this MgBr part is bond. This phenyl group is directly bonded to this carbon, and then on the process of hydrolysis, you can see, my dear students, this double bond turns into double bond O, and we get the propiophenol. This is C6H5. C6H5. So we get propiophenol here, my dear students, or it is also known as the 1-phenyl propane. Why do we call it 1-phenyl propane? Because on the first carbon there is a phenyl group present, and that is why we call it 1-phenyl propane. So this is how, my dear students, from the nitrile even we can easily prepare the ketone of our desire. So whatever the kind of ketone we want to prepare, according to that, we need to choose the Grignard reagent. So the way we choose the Grignard reagent, that kind of product we generally get. Now, my dear students, we can prepare from benzene or substituted benzene. So if you want to prepare from a ketone, generally the phenyl ketone from benzene or benzene substituted benzene, we generally use the Friedal-Craft reaction. In Friedal-Craft reaction, when benzene or substituted benzene is treated with acid chloride, that is your CH3COCl or RCOCl, we should say RCOCl, in the presence of anhydrous aluminum chloride, which is your AlCl3. Please remember, instead of acid chloride, we can even use acid anhydrides. Which are RCO twice into O. This is what it is known as the acid anhydride. So instead of acid chloride, we can even choose acid anhydride to get the desired product, my dear students. Let's have a look to this. See, you can see here in this reaction that benzene is allowed to react with alkyl or aryl acyl chloride. If R is there, then we call it alkyl acyl chloride or aryl acyl chloride. And then in the presence of anhydrous AlCl3, this C double bond, this particular group is bonded with the benzene, and this is how we understand. Let us understand the same reaction with a particular example. If we take benzene and allow it to react with the acetyl chloride in the presence of anhydrous AlCl3, we get acetophenol. This is what it happens. Now, my dear students, we want to understand a few of the in-text questions. So, the first in-text question is about the nomenclature, about the compound that is, or about the reagent that is needed to bring a following transformation. Give names of the reagent to bring about the following transformations. The first one is hexanbanol to hexanal. Hexanbanol to hexanal, that is your alcohol is converted to aldehyde by PCC, that is pyridinium chlorochromate. Then if you want to convert, my dear student, the cyclohexanol to cyclohexanone, you can use anhydrous CrO3. It's a alcohol that has been converted to ketone. Parafluorotoluene to parafluorobenzaldehyde. Here you want to convert toluene to benzaldehyde. So we generally use CrO3 in the presence of acetic anhydride. Apart from that, we can even use CrO2Cl2 and water. This reaction we call it Etard reaction. So this is how it goes, and we ethane nitrile to ethanol. This is nitrile compound. You want to convert it into the ethanol. Actually, it should be ethanol with the present in the presence of the dibyl H. You can easily convert the ethane nitride to ethanol because dibyl H converts the nitriles to the aldehyde very easily. Then allyl alcohol to propanol. So allyl alcohol is converted to propanol. Allyl alcohol is having double bond. This is what it is known as the allyl alcohol. This allyl alcohol can be converted to propanol without affecting this double bond, and that is possible with the PCC, pyridinium chlorochromate. Then butene to ethanol, that is what it is done by the process of ozonolysis. You can see that I have explained you the ozonolysis process. This is butene. This butene, when it reacts with the ozone, it gives the ozonolysis product. This ozonolysis product, it's simply broken in this manner in the presence of zinc dust and water. This, the electron of this bond comes to here. The electron of this bond come here, and here we can have the double bond. So we can have CH3, C double bond O, NH. This is your ethanol. And from this side we get ethanol, from this side we get ethanol, and ultimately we get ethanol as a 2-ethanol molecule as a final product. Now, my dear students, the next question for us, write the structures of the product of the following reaction. Here we have friedal Kraft acylation to be done. We have benzene, we have acyl chloride C2H5COCl in the presence of anhydrous AlCl3. You can see that this group will be bonded to the benzene, and this is how we can get the 1-phenyl propanone or propiophenol. We have already seen why do we call it 1-phenyl propanone. Then, my dear students, here this reaction we called oxymercuration. Here we have Hg plus 2 ion or Hg plus ion in the presence of H2SO4. This simply converts this alkyne into, these alkynes are simply converted to ketones directly here. So you can see that from the propyne we directly get propanol. Same way, my dear students, here we again have the Itard reaction where chromyl chloride reacts with this compound to give a complex, and this complex on hydrolysis gives us the aldehyde. So 4-nitrotoluene will give us the 4-nitrobenzaldehyde by the reaction which is known as the Itard reaction. This is how, my dear students, we solve the various in-text question and exercise question for us. Now, my dear students, we want to study about the physical properties of the aldehydes and ketones. So let's move forward and understand about the few physical properties. The first one, methanol is a gas at room temperature. Remember, methanol, that is your HCHO, is a gas at room temperature. Ethanol is a volatile liquid. Other aldehydes and ketones are liquid or solid at room temperatures. So methanol is the only gas available among the aldehydes and ketones. All the other aldehydes and ketones are either volatile liquid or they are solid in their physical state. Now we should look at the boiling points. The boiling points of aldehydes and ketones, the boiling points of aldehydes and ketones are higher than the hydrocarbon and ether of the comparable molecular mass. Please remember, my dear students, that the boiling point of these compounds are generally the boiling higher are generally higher than the boiling point of the ethers as well as the boiling point of the hydrocarbon of the comparable masses. So this is how, my dear students, we understand about the boiling points of these compounds. Uh, Higher boiling point than ether is because, or highly high boiling point than ether and hydrocarbon can be explained on the basis of weaker intermolecular association due to dipole-dipole interaction. So, my dear students, in aldehydes and ketones, we have weaker dipole-dipole interaction, and because of that, they have the higher boiling point than the uh, higher boiling point than ether and hydrocarbon can be explained on the basis of weaker intermolecular association due to dipole-dipole interaction. Boiling point lower than alcohol is due to the absence of intermolecular hydrogen bonding. So in aldehydes and ketones, the intermolecular hydrogen bonding is not present, and that is why the boiling and melting point is or boiling point are weaker, we can say that. Now we have the name of the various compounds, their boiling point in Kelvin and their molecular mass. You can see that we have chosen the compounds which are having the molecular mass very comparable, very near to each other. Three of them have 58 gram per mole, whereas only methoxymethane has got 60 gram per mole. You can see their boiling point. Boiling point of normal butane, which is an alkane, is 273 Kelvin. This is methoxymethane is an ether. Its boiling point is 281. Propanol, which is an aldehyde, and its boiling point is 322 Kelvin, whereas acetone, which is a ketone, and that has boiling point of 329. So this is how we can easily understand that in this case, the boiling point of acetone is maximum, whereas the boiling point of alkane and ether are lower. But when we look at the boiling point of propanol with the 60 gram per mole molecular mass, it is highest among all of them. And this is how we can understand how the boiling point changes when we move from the alcohol to ketone to aldehyde to ether to the alkane. Even if we want to write the order, we can write it this way, my dear students. Please pay attention that the boiling point of alkane are generally less than ether. Then we can think of aldehyde. Then we can think of ketone. And then we can think of alcohol. In the same chapter, we will study that even as compared to the alcohol, carboxylic acid, they have higher boiling point. So this is how we can understand the increasing order of boiling point for the various functional groups. The lower members of aldehydes and ketones, such as methanol, ethanol, and propanol, are miscible with water. You know, miscible means they are highly soluble, they are soluble in a great extent. So, they are miscible with water in all proportion. They are miscible in all proportion because they form the hydrogen bond with the water. So you can see, my dear students, that methanol, ethanol, and propanol, which is also known as acetone, methanol, ethanol, and propanol, they are highly soluble in water. You can see here that here we have ketone, here we have an another ketone, or you can, if we put here the H, then it can be an aldehyde. So both aldehydes and ketone, they can make the hydrogen bonding with the with their oxygen, or using their oxygen with the hydrogen present in the water molecule, and this is how these lower aldehydes and ketones are highly soluble or are miscible in the water. We can move forward. However, the solubility of aldehydes and ketone decreases rapidly on increasing the length of the carbon chain. So if the carbon chain length increases, that means number of carbon increases, then the miscibility or the solubility decreases. All aldehydes and ketones are fairly soluble in organic solvent like benzene, ether, methanol and chloroform. So all the aldehydes and ketones are soluble in the organic solvents like benzene, ether, methanol and chloroform. The lower aldehydes have sharp and pungent odors. When we smell them, there will be irritation in our nose, and such smell we call them the pungent smell. So, lower aldehydes have pungent smell. As the size of molecule increases, the odor become less pungent and more fragrant. Please remember that slowly as the number of carbon increases, their smell become less and less pungent, less and less irritating, and we would like or we are going to like them, or they give a good smell as the number of carbon increases. In fact, many aldehydes and ketones are used in the blending of perfumes. So remember that many aldehydes and ketones are used in the blending of perfumes, and they are also used to give flavoring agents. That means to give flavor to the food and drinks or beverages, you can say. So the various beverages or drinks which are available in the market, these aldehydes and ketones are used to give them the smell or a good smell or a good flavor. This is how, my dear students, we study about the flavoring or the uses of the aldehydes and ketones, and we have been studying their physical properties. Now, my dear students, let's solve some questions so that whatever the concept we have studied, we can understand it well. Arrange the following compounds in the increasing order of their boiling point. Here we need to arrange them in the increasing order of their boiling point. The first compound is aldehyde, another is alcohol, then we are given ether, and then we are given the alkane. We are all aware that the lowest boiling point would be there with the alkane, and the highest would be there with the alcohol. In between we can compare the ether and aldehyde. Then ether would have the lower boiling point as compared to the alcohol or aldehyde. So you can see that we have the increasing order like alkane, the ether having more boiling point than alkane, aldehyde having more boiling point than ether, and alcohol is having more boiling point than the aldehyde. Same way in the second question, we are given aldehyde, alcohol, ether, and alkane. Again, we would follow the same order, that alkane with the lowest boiling point, then we have ketone, then we have aldehyde, and then we have alcohol. So here now the question arises that why we have a aldehyde having more why this aldehyde is having more boiling point than ketone. This is because of the steric hindrance, my dear students, that we have C double bond O. Here both the side you have alkyl group, but if you look into this R CH3CHO, here R C and here we have H, and then we have double bond O. So that is why the hydrogen bond can be easily formed with this ethanol, and that is why the boiling point of ethanol is more than the boiling point of ethoxy ethane. Uh, it is even it is even the ether. So I think I was so this is how we can easily understand that alkane, ether, aldehyde, and alcohol. Please remember and learn this, my dear students. Then, my dear students, we are going to study about the chemical properties of these compounds. Since aldehydes and ketones both possess the carbonyl functional group, they undergo the similar kind of chemical properties. So first type of chemical properties that we are going to study is known as the nucleophilic addition reaction. Aldehydes and ketones undergo nucleophilic addition reaction. Mechanism of the nucleophilic addition reaction. What happens? We have an aldehyde or ketone with the carbonyl group. This carbon is less electronegative. This oxygen is more electronegative. So there is slightly negative charge on oxygen and slightly positive charge on carbon. Here this is our nucleophile that attacks. Nucleophile is electron rich species. So we can easily understand that the nucleophile will attack on the positively charged carbon rather than the negatively charged oxygen. So nucleophile attacks the carbon. You can see that, or we have already seen that all the bonds of this carbon are present in the same plane. So now after the attack of nucleophile, uh, the sp2 hybridized carbon, this sp2 hybridized carbon simply turns into tetrahedral sp3 hybridized carbon. You can see even that this was the planar structure which turned out to be tetrahedral. You can see this planar structure has turned out to be tetrahedral now because the hybridization has been changed and nucleophile combined with the carbon, and then by the rearrangement or in the second step we have H plus which is available that combines with the oxygen and gives us the addition product. So my dear students, this C double bond O turns out to be CNU and OH. So this is how we will get the addition product. Those two groups which are bonded here and which are bonded here, they remains the same, which we represented with the group A and B. So group A and B remains the same, but carbon now combines with the nucleophile and oxygen get an oxygen is converted into OH group or hydroxyl group. This is the simple mechanism by which we get the various reaction or various the nucleophilic substitution reaction, nucleophilic addition reaction given by the aldehydes and ketones. So let us study this, what we have seen. Nucleophilic attack the electrophilic carbon atom of the polar carbonyl group form a direction approximately perpendicular to the plane of sp2 hybridized orbital of the carbonyl carbon. The hybridization of carbon changes from sp2 to sp3 and thus the planar structure turns into the intermediate tetrahedral alkoxide. This intermediate captures a proton from the reaction medium to give the electrically neutral product, which is an alcohol or final product containing OH group. The net result is addition of Nu and H plus across the carbon and oxygen double bond shown in the figure. Now, a very important point, my dear students, that is about the reactivity. Aldehydes are generally more reactive. Please remember this. That aldehydes are generally more reactive than ketones in nucleophilic addition reaction due to the steric and electronic regions. Sterically, the presence of two relatively large, you can see here that in ketone, around this there are two large molecules available or two groups available, but in aldehyde, only one side alkyl group is there, another side is hydrogen. So attack of the nucleophile become easier from this side. But here the attack of the nucleophile is difficult in case of ketone, and that is why my dear students, we can say that aldehydes are more reactive than ketone for the nucleophilic addition reaction. That is what we have studied the sterically. Sterically, the presence of two relatively large substituent in ketone hinders the approach of nucleophile to the carbonyl carbonyl aldehyde having only one such substituent, and then we should understand electronically that electronically aldehydes are more reactive than ketone because two alkyl groups reduces the electrophilicity of the carbonyl carbon. Suppose this carbon is positively charged and two alkyl group gives them the electron, but this carbon is positively charged and one side only hydrogen and another side only one alkyl group, which is electron donating group, gives them electrophilicity. So here the electrophilicity of this carbon decreases. Here the electrophilicity of this carbon is more, and that is why electronically even the aldehydes can give a better product, or aldehydes are more reactive than the ketones. So my dear students, let's revise what we have studied today in today's class. Let's have look to the various things that we have studied. We have studied about the preparation of ketones. We have studied the preparation of ketones from the acyl chloride by using the CdCl2. CdCl2 converts grignard reagent into dialkyl or diaryl product, which in turns react with the acyl chloride to give us ketone. From nitriles in the presence of grignard reagent, we get the complex on hydrolysis. That complex gives us the aldehyde or ketone. Same way, my dear students, we have studied about the preparation of ketone from benzene by the friedal alkylation. You can see here, benzene reacts with the acyl chloride or acetic anhydride in the presence of anhydrous AlCl3 to give us the uh, uh, ketone of our desire. We have studied about the physical property and we have seen that methanol is the only gas among all the aldehydes and ketones. All the other aldehydes and ketones are volatile liquid or solids. The boiling point of aldehydes and ketones are higher than that of the uh, ether and alkane, but they are lower than the alcohol. And these aldehydes and ketones, they have weaker dipole-dipole interaction, but the hydrogen bonding is not present in the aldehydes and ketone, and that is why they are they have lower